Dear students, welcome to the lecture series of digital electronics. And in sequential circuit, today we will discuss the serial adder. As we know that in digital computer mostly done in parallel operation because it is a faster mode of operation. Serial operations are slower, but it requires less equipment. The main advantages of serial operation is require less equipment. This is the main advantages. And to demonstrate the serial mode of operation, today we will discuss how we can design the serial adder. Parallel adder is a combination circuit which we already discussed. And in serial circuit, the inputs are coming in serially. Suppose there is a two inputs, so A and B are coming in single wire, whatever the length. It may be 8-bit length or it may be 4-bit length. Whatever that thing, the sum and carry two outputs are generated and both are serial. So input and output all are serial, and this we can design. Normally, as a human mind, we do that thing serially in our mind operations as we learn in school level. So there is a two way of serial adder. One is using the full adder, and second one is using the flip flop. So let us start with the full adder. The circuit is now so that serial adder with full adder circuit. Full adder we use here. Combination circuit is that. This is D flip flop. We have a two register, shift register and register B. So the operation is that register A plus register B is generated and it will store in register A. Okay. So now the A is equal to A plus B, the previous value of A and the value of B. This thing we will do it. Externally input also connected here. So there is a two register A and register B is that. So serial input is that. Here A will be remain same. B is input here. So let this will be take a B. So here the B result A plus B, A is equal to whatever the A content plus B content is that. And serially input is also insert in B. So might be B will be changed. Let's do how it can be possible. So the output of the flip flop is then used as an input carry to the next pair. Okay, input. Why we take it? Because the sum will be also helpful for the next carry. The two shift registers are shifted to right side. So always in each every clock pulse, of one bit shifted to right hand side, and the sum bits from the S output full adder could be transmitted into third shift register by shifting the sum into A while bits A is shifted to out and serial input to register B. Every time the register B serial input is given, this serial input is the sum result is that. So result will be stored here. The final result will be stored into the disk. New binary number while the added the bits are shifted to during the operation. The operation of the serial adder is, let's start. The initial value A is holds the added and B is holds the added thing is that. So let's understood the behavior of this circuit, and we take the one simple example how it can be operate. Suppose here the initial value is 000, but this is the excitation table. Okay, now how it can be worked? So first is that the operation serial register A is a gun, while added is register B. Okay, and then the carry flip flop is clear to 0 first. Second thing is that the serial output SO of A and B provide a pair to significant bits for the full adder X and Y. Here serially one come. The Shift control enables both the register and carry the flip-flop as the next clock pulse both registers are shifted once to the right and the sum bit of S enters to the leftmost flip-flop A and the output carry is transferred into the flip-flop Q. Remember that thing, the shift register control enable the right shift. The number of clock pulse is equal to the number of bits in register. So for suppose there is a 4-bit register and this is also, so 4 clock pulse is required to complete the operation. A new carry transfer into Q, both registers are shifted once to the right. Every time whatever the carry is generated is stored here and it will be helpful for the next stage. Okay, in next stage carry. Whatever the present state carry, it will be useful in next state carry by this operation. Feedback is there. And for temporary storage, the D flip flop is used here. The process continues until the shift right control is disabled. Thus, the addition is complete. Now, shift right, this shift right will become the 4 clock pulse width is required to complete this operation. Okay, so shift right is enabled for the 4 time. 1, 2, 3, 4 time T. This is called as a shift right control signal control panel C. Okay? That's understood. Suppose the input is register A 0101, register B 0111 is there. So what happens on the first clock pulse? The first clock pulse, the value of X and Y is SO. SO is 1. This is also 1. And initial carry, there is no output, so 0. So 1 plus 1 plus 0 is, there is a 0 is the sum and carry is the 1. So this 0 will be shift here. Okay, so register A, it will become now 0 and these 3 bits are there 0, 1, 0. Okay, this is the sum output. On the carry is 1, so then D will become 1. Now, on the second clock pulse, on the second clock pulse, the here, the second bit 0 and 1 is here, 0, 1. On the clock pulse, the Z will become 1 because this is the combinational circuit. So after the clock pulse, this will become generated. Clock pulse is here connected, both are ended and connected via this gate number 1. So on the clock pulse, it will become 0 plus 1 plus 1. Again, the result carry is 1 and sum is 0. So this will be transferred here. The second bit, this will become removed. And this one remains stable. Now the third one, third clock pulse. On third clock pulse, the input is 1, 1. And at that time, the previous output clock pulse, it will become 1. So finally, the input is 1, 1, 1. The result is 1, 1. Sum is 1, carry is 1. So this will become in SI and register A contained. Here 1 is added and this one is removed. Okay. Now again, after that, the next is 0, fourth clock pulse. 0, 0. And the carry, previous carry is 1. On clock pulse, this 1 will become transfer here. So the result will become carry is 0, sum is 1. So this one will be go here and last bit is removed. So final result is register A. Now register A is equal to 1, 1, 0, 0. Let's see 1 plus 1 0, 1 plus 0 plus 1 0, triple 1 1 and 1. So this result will store into register A. In this way, the new number has added into the content of register A, and this number is AB first transfer serially into register B. So repeating this process more will add the second number to previously number number A. Okay, so in this way, the register B will become external input, or if it is 0, so register B value will be changed, but register A is equal to register A plus register B. Then after clock pulse, A is equal to A plus B. So it is called as a serial adder circuit. So comparing the serial adder parallel adder, the first thing is that the parallel adder must be registered with the parallel load capability. While the serial add use the shift register. The number of full adder circuit in the parallel order is equal to the number of bits. Suppose there is a 4-bit parallel adder circuit, 4 full adder circuit is required, and additional combination. While in serial, excluding register, parallel is purely combination circuit, and in serial adder is a purely sequential circuit. The sequential circuit is in serial adder consists of a full adder plus flip-flop. The output is a carry. So this is a typical serial operation because the result of a bit time operation may depend only on the result inputs of two previous inputs. To show the bit operation serial adder, computer may require sequential circuit. So let's design another serial adder with the help of combinational diagram. And this is the here present state and next state. What we are doing, the present states and next state here. So this is a serial adder circuit. Here, what happens? The circuit excitation table is given. By present state? Present state input is this 0 plus 0, and Q is there. It is a carry, previous carry. And this output is sum, and next state is a carry output, sum output. Okay, so 0 plus 0 plus 0, 0, 0. 0 plus 0 plus 1, 0, 1. 0 plus 1 plus 0, 0, 1. 0 plus 1, 1, 1, 0. 1 plus 0 plus 0, 0, 1. 1 plus 0 plus 1, 1, 0. 1 plus 1 plus 0, 1, 0. 1 plus 1 plus 1, 1, 1. So this is simple adder. Sum and carry two outputs are there. Okay. Now, after that, excitation table is required. Okay, this table. How this table is come? Comparison of Q and this. 0, 0, so 0x. 0, 0, 0, 0. In three condition, 0 zeros are there. So in three condition, 0x is that. K, J must be 0. If K is 1, reset, or K is 0, previous state. Here, 0, 1. So 0, 1 require J1 and X, K as per excitation table. In below, next is 1 and 0 is that. So 1, 0, there is require X1. And last 3 bit 1, 1. So that means the K input must be 0, X must, J must be X. So as per the excitation table, we obtain that things. Now, from this, require the equation for JQ and KQ. So we obtained that only in one condition, the JQ is 1, 0, 1, 1. And remaining one condition, we last four condition, it's not here. So we can say that JQ is equal to XY. KQ is equal to here, KQ. KQ here and 1. So KQ is equal to X dash Y dash, and this is XY. X dash Y is this De Morgan's theorem, X plus Y whole dash, NOR gate is there. And S is equal to, as usual, this is the exclusive OR of X, Y, and Q. Okay. So for that, we have designed two shift register. JK flip flop is that, as we know that J is equal to XY. So this is X and Y. This is X, Y whole dash. And the clock pulse is the common clock pulse of both the shift right and clock pulse, both are enabled, and sum is equal to exclusive of X, Y, and Q. So this is simplest circuit with the help of JK flip flop and combinational circuit. Full adder is not required. So in this way, we can design the full adder circuit with the help of flip flop or with the help of combinational circuit.